And Matt, you all know Matt. If you don't know Matt, you weren't here last time, but you should know Matt. He's really good, and he's going to do the second lecture. Yay!
Okay guys, so the second lecture is all about inputs to the Arduino. So last time we were covering what you can do on the outputs, all the different LEDs, that kind of stuff. So now, how can you actually interact with it to control it? So there's two main types of signals that we can deal with here. You've got digital signals and analog signals. In the case of the Arduinos, the digital signals are 0 and 5 volt. So they represent binary 1 at 5 volt and binary 0 at 0 volts. Analog signals are a bit more interesting and irritating to work with because they can have literally any value, well, at all. The Arduino can cope with any value up to 5 volts and can actually read it in through the analog to digital converter, which we'll talk about in a minute. So first off, digital signals. So as we said, there are only two possible values for the Arduino system. It's between 0 and 5 volts. There are other variations of Arduino boards that might run on 3.3 volts, and other microcontrollers do as well. Those are the two sort of standard voltages you'll be running at. But either way, 0 is always your binary 0, and whatever your high voltage is for your system is your binary 1. Yeah, as I said, not all of them use 5 volts. A lot of them will break if you put 5 volts into them. All the kits you've got will run at 5 volts without a problem. So analog signals, not spelt the American way. Analog signals can have any value. In terms of the Arduino, we can read up to 5 volts, as I said. And there are two different sections of information basically contained within an analog signal. You can have both the level and the frequencies of the signals. So as you can see, this has a particular frequency of repeating, so you can get something some more complex data into it. The Arduino can read the analog signals, but as we discussed last time, it can't output pure analog. So it actually outputs a PWM waveform, which we'll talk about in a moment, to basically pretend to be analog, which is how you were fading the LEDs last time. It just tricks your brain. So this is actually what PWM looks like, pulse width modulation. It pretends to be analog basically through averaging. So for a 50% value, it will be halfway between your 5 volt maximum and 0 volt. So it will average out to 2.5 or half brightness if you're connecting it to an LED. Again, if you turn it on for more of the time and off for less of the time, you can get a higher average, a lower average, and off if you just turn it off entirely. The timing between the rising edge of all of these is always fixed on the Arduino. It's set within the controllers. You can change it, but that's quite complex and usually you don't need to. It changes the value simply by changing how long it is physically on for within that time. So here we've got an example of outputting. This is outputting a digital signal, but in this case we're cheating it slightly to output a tone. So built into the Arduino system we have the tone library. This allows you to output the PWM waveform. It outputs it at 50%, so half the time on, half the time off, but it changes the frequency that it's doing it at. So by doing this you can output different notes. Yeah, this tone library allows you to do it very simply. Simply put, you can start a tone by telling it what pin you want it on and what frequency you want it to run at. If you want it to stop, you just put no tone, whatever pin it was. This doesn't necessarily work on every single pin. I'm pretty sure it has to work on the PWM pins only, so the ones on your boards with the little squiggle next to them, which I can't remember specifically which ones they are. It's 2, 3, and a few others up that row. So that example we have here, simple increasing tone. It'll go from a low 400 Hertz frequency, ramp up to 1.5 kilohertz. You should have this example on the sheets you've got that came around. Okay, so the next thing would be to have a digital input to the system. Digital inputs are input values, binary, high and low, just a simple signal. This is a very simple piece of code to read a button. So you should have buttons like this in your kits that you can play around with in a minute. And you set them up using the same pin mode as we used before and set them as input. Now this input pull-up is a slightly different variation on it. What this allows it to do is it attaches a resistor, pulling it between the pin that you've got connected to it and 5 volts. This means that when you're not pressing the button, that pin is latched high. And then if you connect the button between that pin and ground, as it is on here, when you press the button, it pulls the pin low, and you can read the values like that. This helps you. This is built into the chip on the Arduino, so this helps you to minimize the number of components you need externally. Yeah, so to read this, simply put, you just use the function digital read with whatever pin you're using. And then you can store that into an integer or a Boolean, any of the data types basically, because it comes out with a 1 if it's high, a 0 if it's low. So here's a slightly more complex piece of code. You can have a go at it in a minute. This piece of code is used to toggle an LED. So what we have, you've got your standard sort of setups, defining some pins, and the current state of the LED, the current state of the button. So what we do is we loop around reading what the pin is. Then we check if the pin has changed. This exclamation mark equals is if it's not equal. So if the button pin has changed, you store the new state. If the button is low, so if you are in fact pressing the button, you can then toggle the LED state. Yeah. The exclamation mark simply means not. So you set the LED state to the opposite of whatever it is now. And then you just write it out as, you write out to your LED pin the state, so you turn the LED on or off depending on what that value is. Again, you'll have a go through this in a minute. Now, the problem we have is that in the real world, nothing's quite that simple. So you don't get this sharp edge change. Instead, you get something like this. This is quite a small time scale, 2 milliseconds per division. So basically, when you press the button, you get this kind of thing happening as the button bounces slightly. This can cause a problem because your microcontroller is running at 16 megahertz. So it can very easily pick up all of these bounces and flash your LED on and off far too much. This means that you've got to actually deal with it in the code or somewhere in there so that you can stop it from having that effect. It's relatively easy to do, but it's something that usually messes up your systems quite a lot. So this is slightly more complex code, probably a bit difficult to read from there. It should be on your sheets. Yep, it's on the back of your sheets. So this simply loops through. It's doing exactly the same thing, but it has this extra little bit of the debounce time. So this is using the millis function on the Arduino. This is a function that will return an unsigned long integer, which is up to some ludicrously large number that I can't remember, of how long the Arduino has been running since you started up in milliseconds. So this is very useful for seeing how long it is since the last thing happened. So simply put, if the button has been pressed, you store the time that it was pressed into this variable. Yeah, if you then take the current time minus the last time it was pressed, if it's greater than your delay, so this is a value you can set up the top. In this case, it's set to 50 milliseconds. So that means it will ignore any repeated signals within that time frame. And then you can do your standard code for toggling LED or whatever it is you want to do. So by combining these two statements, you can very easily stop it from doing this bouncing behavior. And this is something you just throw into your code all the time. So before we move on to the analog inputs, we'll just have a quick go with this stuff. If everyone wants to actually have a play with these, just get some buttons hooked up, get them actually reading in, and make sure that's working, and then we'll move on to reading analog values. Hey guys, so we've got a couple of slides left on here, just a few more things. I know some of you have been playing with it already. We'll carry on afterwards. So the last thing we've got for the inputs is the analog input. So this uses an analog to digital converter built into the Arduino chip. What this allows you to do is to measure values between 0 and 5 volts, and it splits them down into steps. So it has 1024 steps in that range. Slightly strange number, but it's 10-bit analog to digital converter. So to read an analog value, use Analogue Read for whatever pin it is. And this works with the analog pins that are on the opposite side to most of the pins you've been using. They're labeled A0 through A5. And you put those in, just literally type A0 into it, or whatever one you happen to be using. So this function returns whatever value it is, which is proportional to the voltage. From this, you can do more complex things. So you can set So you can set an analog write, so if you want to use it to set the brightness of an LED, you can directly output it to that. This mapping function is an incredibly useful function of the Arduino. So what you can do is you can map a value that comes out between two ranges. So you've got your potentiometer value that's read in here, is between 0 and 1024. You can then map it to a completely different range, which can be backwards, it can have negative numbers, whatever you like. So this means that it basically changes from 0 to 1024 to 0 to 255. You should have this code on your sheets if you can't read it off the board. So what this means is that by doing this, we can put it into the analog write function in this case, because the analog write function is 0 to 255 for the full range. So you can convert it into whatever range you want to use. So for this, using potentiometers, you should have them in your kit. Some of them might be missing. And basically, they have 3 pins on them. One of them you connect to 5 volts, one to ground, and the other one is the pin that is actually sweeping between the two. So this is effectively 2 changing value resistors, so it's a voltage divider, and it sweeps along, setting value each side, being proportional to the voltage. The ones you've got should look vaguely like this. You should have 2 pins on one side and 1 pin on the opposite side. The pin on the opposite side is your output. And you connect that straight into one of your analog pins. So with that in mind, there are some more interesting things you can do. A lot of you have been messing with the buzzers and the LEDs and buttons at the same time, but you can link the LEDs to the analog pin, do something with that, and there's a nice, slightly complicated one at the end to make a combination lock. So setting analog values to pretend to be the wheel of the lock. That's a challenge you can have a go at. And of course, all the other ones will still be helping you with you. And apparently there's a dog on this slide. I don't know what he's doing there. Yeah, so if you want to have a go with those, we'll still be around answering any questions.